Hello everyone, so we are Team 4 and we are going to present our recent progress on the microsystems development. So first is our overview of the current status. First, we are continuing the fabrication process, and at the same time, we are uh, optimizing the wireless systems for the final performance test of the fabricated diaphragm and sensors. And to continue with last time, we are making the first photolithography process to make the open window pattern. Use the AZJXR uh, PR to make the open window pattern, and then we are going to each to control the thickness of the silicon wafer. So first, we are using the BHF etching process to remove the silicon dioxide of the open window pattern. Then we are going to conduct the TMH etching process to remove the silicon dioxide, to remove the silicon and control the thickness of the silicon. And first the figure shows the silicon wafer combined with the jig for the TMH etching, and second shows the setup of the TMH etching process. As you can see, the temperature we used is 80 degrees of the solution. And this video is just showing the bubbles will be generated when conducting the TMH etching process. And the TMH etching rate is 0.5 micrometers per minute. And where our expected thickness is 14 micrometers of the final diaphragm. So we took the etching time for the 80 minutes. And finally, we have checked the thickness and the surface profile. And after that, we are going to generate another silicon dioxide layer to protect. So we just conduct the same process as last time to make a 300 nanometers dioxide layer on the silicon wafer's surface. And after that, we are going to make the sensor pattern on the silicon wafer. So this time we are going to use the spatter method to deposit the chromium at the sensor layer. And here just shows the equipment and the principle of the spatter deposition. We're going to use the air ions to heat the metal target of the chromium. Then the chromium ions will falling down onto the substrate and the film will be gross. And our expected thickness is the 200 nanometers chromium layer. And here just shows the real condition of the sensor deposition and the patterning process. First shows the sputter target connection of the chromium, and there is a film mask for the sensor patterns. And then we just conduct the photolithography using the AZJAX RPR to make the sensor patterns. First is the spin coating, then UV exposure, and then develop to make the PRS pattern as shown at the left bottom side. And after that, we will conduct the chrome etching process to make the uh, sensor pattern. And after remove the PR, we will get the final sensor on the surface. And except the fabrication process, we also continue to optimize the wireless system. And since last time, for the test, we didn't get the purchased components yet, so we just did some basic test. But this time we have got the new components for our expectation, so we'll build a more complete system for the real test. As we can see, the red figure is showing the setup of the system with the two Arduino board to conduct the RF communication, and also we have integrated with the OP amplifier to gain the output voltage signals. And here this video is showing the real-time signals, and the system uses an OP amplifier HX711 to amplify the signal, with the gain value is 128. And the issue is we can see so many big peaks generate as the time goes by because the big noise is introduced due to the large signals. because as we can see, the OP amplifier HX711 is designed especially for some small signals, but the existing current system is too large for the proper application. So we are expecting that it will be more suitable for fabricated sensors. Additional work is required for initial calibration and setting an operator gain value for the final real system. And this slide is showing the environment setup, especially for the communication and the program part. First, the transmitter and the receiver are both of the Arduino RF communication, and for and at the same time we are using the Python codes to achieve the real-time plotting and the serial communication and CSV data save, this kind of functions based on the Python systems. And here this slide we are showing two videos for the test and the real-time plotting of the setup the system. As we can see, the left side is the setup of the system, and we are using a commercial four commercial resistors conduct a full Western bridge circuit, and then we adjust one resistance value and detect the output voltage. And now the system can use RF communication to detect the real-time output voltage signals. As you can see, the blue line is the output voltage, and also at the same time, the system will calculate the real R4 value of the full Western bridge circuit. And compared to our previous test, it is obvious that we can see the frequency is much better than before, and at the same time, the noise issue is much better. So we can imagine it would be more proper for our final sensors performance test and the output voltage detection. And also we're considering about the bias voltage if it will be better to get higher output voltage signals. And this slide is a conclusion about the final systems application. First, we will achieve the real-time plotting as we just showed to detect the output voltage signals in the real time. And the second, we can save the data of the recorded of the real-time recording. And the third part is the real-time online update, so that we can update the signals data online, and we can download even we are not by the samples side or even far away. We can also get the data. I think that part is more desirable and the most important. Okay, so Uh, these are our existing progress on the whole systems. And the next step, we are going to finish the fabrication process and finally combine with the performance test, combine with the wireless system to conduct the performance test of the fabricated diaphragm and the sensors. Okay, thank you so much for listening.